Welcome to the next stage of problem solving session of this polymer reaction engineering. Now let us start with the problem number 1. Here the rate of liquid phase reaction, which is having the type of A plus B is equal to P, is found to be the independent of concentration of A and B, which is equal to 1 kilomole per meter cube minute at 300 Kelvin. Now you need to find the conversion in a mixed flow reactor, which is having the volume equal to 2 meter cube with the feed concentration of A and B both are equal to 5 kilomole per meter cube and feed rate is equal to 1 meter cube per minute. The reactor temperature is equal to 300 Kelvin, and if the activation energy of reaction is given as 83.1 kilojoule per mole. Again you need to find the volume of an isothermal plug flow reactor for the same conversion and the feed conditions as in the case of above mentioned reactor, but with the reactor temperature which is maintained at 320 Kelvin. So let us try to attempt this particular problem. Now for mixed flow reactor, the tau is equal to Ca naught minus Ca upon minus Ra, and which can be represented as V upon V0 Ca naught minus Ca upon minus Ra. Now here the given parameters are V is equal to 2 meter cube, V naught is equal to 1 meter cube per minute, minus Ra is equal to 1 kilomole per meter cube minute, Ca naught is equal to 5 kilomole per meter cube, and 2 upon 1 is equal to 5 minus Ca upon 1. So if we write that Ca, what is the value of Ca? That is Ca is equal to 3 kilomole per meter cube. Now for conversion Ca is equal to Ca naught 1 minus Xa, and Xa is equal to 1 minus Ca upon Ca naught. So Xa will come out to be 1 minus 3 upon 5 equal to 0.4. So given that the rate of reaction is found to be independent of concentration of reactant A and B, so the given reaction is a zero order reaction. So that is, if we say that it is a zero order reaction, then in that case minus Ra is equal to K. So from Arrhenius law we may have this Ra minus Ra is equal to K naught e to the power minus E upon RT, and that is 1 is equal to K, that is equal to K naught e to the power minus R E upon RT, and we can find out K naught is equal to E to the power E upon RT, and that comes out to be 83.1 into 10 to the power 3 upon 8.314 into 300, and that the K naught comes out to be e to the power 33.3 kilomole per meter cube per minute. Now for volume of plug flow reactor, the performance equation for plug flow reactor is given as tau is equal to Ca naught 0 to Xa dxa upon minus Ra. So V upon V naught is equal to Ca naught 0 to Xa dxa upon minus Ra, that is V is equal to V naught Ca naught 0 to Xa dxa upon K naught e to the power minus E upon RT, or V is equal to V naught Ca naught Xa upon K naught e to the power minus E upon RT. So if we substitute all the values, then we can find the volume of the plug flow reactor as V is equal to 1 into 5 into 0.5 if you recall the problem, then divided by e to the power 33.3 into e to the power 83.1 into 10 to the power 3 upon 8.31 into 320. 320 is the given. Now V is equal to 0.249 meter cube. This is the volume for the plug flow reactor. Now let us take another problem, that is acetaldehyde A decomposes to the methane B and carbon monoxide C according to the irreversible gas phase reaction. A is converting into B and C. Now 1 kilomole of A is to be decomposed at 527 degrees Celsius and 1 atmosphere pressure in PFR. You may say that this is the first order kinetics. So the first order rate constant K is given 0.5 second inverse. Now you need to calculate the volume of the reactor for 40% decomposition of A. So we are provided with the reaction. Now this is the irreversible gas phase reaction. So the expansion factor or epsilon A, that is given by 2 minus 1 upon 1, that is equal to 1. That is epsilon A is not equal to 0. So the varying volume system. Now since this is equal to comes out to be 1, so this is not equal to 1, so you may say that this is the varying volume system. Now it is given that we are dealing with the first order reaction with the K is equal to 0.5 per second. So V naught is equal to 1 kilomole per second and T is equal to 527 degrees Celsius plus 273, that is 800 Kelvin, and XA is equal to 0.4, that is you need to calculate the volume. Now in that case V naught is equal to 1 into 22.4 into 800 upon 273, or V naught is equal to 65.64 meter cube per second. Now if we talk about the varying volume system, in that case V is equal to V naught 1 plus epsilon A XA, or V is equal to V naught 1 plus XA, that is because we have already find out the value of epsilon as 1. So the rate for decomposition of a reactant A can be written as minus RA is equal to KCA. Now minus RA is equal to KCA naught 1 minus XA upon 1 plus epsilon A XA. So minus RA is equal to KCA naught 1 minus XA upon 1 plus XA, that is for epsilon A is equal to 1. This can be my equation number 1. So when we talk about the performance equation, so performance equation of PFR, performance equation for PFR can be written as tau is equal to V upon nu, that is CA naught 0 to XA dXA upon minus RA, and that is equal to CA naught 0 to XA dXA 1 plus XA upon KCA naught 1 minus XA. So V upon V naught, that is equal to tau, that is equal to 0 to XA into 1 plus XA upon K into 1 minus XA dXA. So tau is equal to V upon V naught, that is equal to 1 upon K 0 to XA 1 plus XA upon 1 minus XA dXA. So if we integrate the things, then we may have tau is equal to V upon nu naught, that is 1 upon K 1 minus XA minus 2 ln 1 minus XA 0 to XA, and that is equal to 1 upon K 1 minus XA minus 2 ln 1 minus XA minus 1, and that is equal to 1 upon K XA plus 2 ln 1 minus XA, or V is equal to V naught into minus 1 upon K into XA plus 2 ln 1 minus XA. So if we substitute all the values, then V is equal to 65.64 into 0.5 1 upon 0.5 minus into 0.4 plus 2 ln 0.6. Now V will become 81.61 meter cube. Now this is my answer, and this is the required volume for plug flow reactor for 40% conversion. Now let's take another problem, that is for a second order liquid phase reaction, A is converting to P. Now occurring this particular thing in an isothermal plug flow reactor, the conversion is 50%. Now you need to find out that what will be the conversion if the plug flow reactor is replaced by CSTR in the same volume. So let us take the cognizance of this particular reaction. A is converting into P. So the rate equation for the second order, because it is given that second order. So the rate equation for the second order can be given as minus Ra is equal to K Ca square, and that is minus Ra is equal to K Ca naught square 1 minus Xa square. So this is my equation number 1. So when we write the performance equation for PFR, then tau is equal to Ca naught 0 to Xa dxa upon minus Ra, and tau is equal to Ca naught 0 to Xa dxa upon K Ca naught square 1 minus Xa square. That is from the equation number 1. So if we integrate this particular equation, then we may have tau is equal to 1 upon K Ca naught 1 upon 1 minus Xa minus 1, and tau is equal to 1 upon K Ca naught 1 upon 1 minus 0.5 minus 1, that is equal to 1 upon K Ca naught, and tau is equal to 1 upon K Ca naught. That is my equation number 2. So similarly, the performance equation for MFR, that is tau is equal to performance equation for MFR, tau is equal to Ca naught minus Ca upon minus Ra, and this particular equation we can say that this is equal to Ca naught Xa upon minus Ra. That is my equation number 3. Now how it can achieve, that is Ca is equal to Ca naught into 1 minus Xa, and that comes out to be Ca minus Ca naught is equal to minus Ca naught Xa, and Ca naught Xa is equal to Ca minus Ca naught. So from equation 3 and 1, we may have tau is equal to Ca naught Xa upon K Ca naught 1 minus Xa square, and tau is equal to Xa upon K Ca naught 1 minus Xa square. So this equation, if we take all the things into coordination, then we may write Xa upon 1 minus Xa square. That is my equation number 4. So for same value of the mixed flow reactor, the tau will become 1 upon K Ca naught. That is from my equation number 2. So if we take the equation number 4, this one, and equation number 2, then we may have 1 upon 1 is equal to Xa upon 1 minus Xa square, or 1 minus Xa square is equal to Xa, or this may become 1 plus Xa square minus 2Xa is equal to Xa, or Xa square 3Xa plus 1 is equal to 0. So Xa, this is the cubic root equation, so Xa is equal to minus 3 plus minus 3 square minus 4 into 1 upon 2 into 1, and if we calculate the final value of Xa, that is comes out to be 2.618, 0.3 0.3819. Now in this the most feasible, because this one is more than 1, so this one is most feasible. So XA is equal to 0.3819, and that is my answer. Now we have nullified this this root just because it is more than 1. Now let us take another example. Now here the substance A in the liquid phase produces R and S by this following reaction. Now the feed having Ca naught is equal to 1 and Cr naught is equal to 0 and Cs naught is equal to 2.3. Now this enters into two mixed flow reactor in series. The values of tau 1 and tau 2 they are given, that is 2.5 and 10 minute. The given composition, the first reactor is given like this, that is Ca1 is equal to 0.4 and Cr2 is Cr1 is equal to 0.2 and Cs1 0.7. Then you need to find the composition leaving the second reactor. Now it is given that we are having the two MFR in series. So let us first the advisable to have a pictorial representation. These are my two MFR. Now here the tau is given 2.5 minute, and then Ca1 this is 0.4, Cr1 it is equal to 0.2 and Cs1 that is 0.7. This is my 2 and 1, and here the Ca naught is equal to 1, Cr naught is equal to 0 and Cs naught is equal to 0.3. So you need to find out Ca2, Cr2 and Cs2. So for MFR1, this is my first reactor and this is my second reactor. The performance equation for MFR1, the performance equation tau is equal to Cr1 minus Cr naught upon K1 Ca1. Now this can be 2.5 equal to 0.2 minus 0 upon K1 into 0.4, and that K1 comes out to be 0.5. This is for R. Now for S, the tau 1, that is Cs1 minus Cs naught upon K2 Ca1. Now if we substitute the value 0.7 minus 0.3 upon K2 is into 0.4, this is comes out to be 0.5. So K2 is equal to 0.4. Now for the second MFR, the stream exit from the first MFR is the feed stream for the second one. So tau 2 is equal to Ca1 minus Ca2 upon K1 Ca2 square plus K2 Ca2. Now let us put all the values. 10 is equal to 0.4 minus Ca2 upon 0.5 Ca2 plus 0.4 Ca2. Now if we substitute all the values and rearrange all those things, then we find that it is 5 Ca2 square plus 4 Ca2 plus Ca2 minus 0.4, this comes out to be 0. Now if we solve this particular equation, we have Ca2 is equal to 0.0745, and that is my answer, first answer. Now for R, we are having tau 2 is equal to Cr2 minus Cr1 upon K1 Ca2, and if we substitute the value 10 is equal to Cr2 minus 0.2 upon 0.5 into 0.0745, and that is Cr2 is equal to 0.2278. That is my answer number 2. Now similarly, if we talk about for S, then tau 2 is equal to CS2 minus CS1 upon K2 CA2, and if we substitute all the values, then it comes out to be 10 is equal to CS2 minus 0.7 upon 0.4 into 0.0745, which we already determined. Then CS2 would be 0.998. That is my answer. So by this way we solved all these things which are needed. Now let us take another problem, that is problem number 5. Here the liquid reactant A is decomposes as per this following scheme, and the rate is given like this. A feed of aqueous A, that is initial gradients are given, that Ca naught is equal to 40 mole per meter cube. This enters into a reactor, decomposes, and the mixture of A, R and S are coming out. Then you need to find out the CR, CS and tau for XA is equal to 0.9 in the plug flow reactor. So let's solve, and it is advisable that every time when you need to solve this thing, then you draw a rough figure. So let us draw the rough figure of my plug flow reactor, that is XA is equal to 0.9, CR you need to find out, CS you need to find out. Here the XA naught and Ca naught is given 40 mole per meter cube. So the rate of formation of R, that is R is equal to K1 Ca, and K1 is equal to 0.4 meter cube per mole minute. So rate of formation of S, Rs is equal to K2 Ca, and K2 is equal to 2 minute inverse. Now for desired product S, the instantaneous fractional yield, we discussed this in this one. So instantaneous fractional yield psi is given as Rs upon Rr plus Rs, and that is dCs upon dCr plus dCs. Now psi S upon A, that is equal to K2 Ca upon K1 Ca square plus K2 Ca. Now it comes out to be 2 into Ca upon 0.4 Ca plus 2 Ca, or psi S upon A, that is equal to 1 plus 0.2 Ca. Now for PFR, that is psi S upon A is equal to minus 1 upon Ca naught minus Ca, that is Ca naught to Ca psi dCa. Now here we are having Xa is equal to 0.9 and Ca is equal to Ca naught 1 minus Xa, that is 40 into 1 minus 0.9, and Ca is comes out to be 4. So psi S upon A, that is equal to minus 1 upon 40 minus 4, 4 to 40 dCa upon 1 plus 0.2 Ca. And if we substitute all the values upon integration, so this is 1 upon 36 into 0.2 ln 1 plus 0.2 Ca 4 to 40, or 5, this comes out to be psi S upon A comes out to be 0.2235. So for final concentration of desired product would be Cs is equal to 5 psi, this is psi, Ca naught minus Ca, and that is 0.2235 into 40 minus 4, and this Cs comes out to be 8.047. Now if we say for the other, for R, then Cr is equal to 1 minus psi into Ca naught minus Ca, and this Cr is equal to 1 minus 0.2235 into 40 minus 4, and Cr comes out to be 27.954. And if we need to find out the tau is equal to Ca naught Ca dCa minus Ra, that is 4 to 40 dCa upon 2 Ca plus 0.4 Ca. Now this is 0.4, 4 to 40 dCa upon 5 Ca plus Ca square. Now if we substitute all the values, then it comes out to be 2.5 into 1 upon 5 ln Ca upon Ca plus 5, and tau is equal to half ln 2. This is 0.347. This is my answer. Now let us take the last example of this particular lecture. Here a well stirred reaction vessel is operated as a semi batch reactor in which it is proposed to conduct a liquid phase first order reaction of type A is converting into B. Now the reactor is fed with the reactant A at a constant rate, which is given to be 1 liter per minute, having the feed concentration equal to 1 mole per liter. Now the reactor is initially empty, so you need to find out the conversion of reactant A based on moles of A fed at time t is equal to 2 minutes. Now the K is given as 1 meter inverse. So first here we need to find out, we need to write the material balance for reactant A. So material balance for reactant A, that is input plus output, sorry, input is equal to output plus accumulation plus disappearance. So if we try to write the mathematically, V naught Ca naught is equal to 0 plus d upon dt Vca plus minus Ra V, and V naught Ca naught, this is equal to V dCa upon dt plus Ca dV dt plus Kca V. Now this is because V is equal to V naught plus V naught t, and this V is equal to V naught t if we put this equal to 0. So we can write this as nu naught V naught Ca naught is equal to V naught plus dCa dt plus Ca d dt plus Kca t. So finally we can write that Ca naught is equal to T dCa upon dt plus Ca plus Kcat, or d dCa over dt plus 1 plus Kt upon T. Ca is equal to Ca naught upon T. That is my equation number 1. So this equation is the form of you can say dy over dx plus py equal to q. So we can write If is equal to p dx. Now p is equal to 1 plus kt upon t, and this is equal to Ca naught upon T. So when we talk about the integration factor, this If can be represented as exponential of 1 plus kt upon T dt Now this is equal to dt over t plus k dt, and this can be written as e to the power ln t e k t. So integration factor, that is equal to t into e to the power k t. Now if we talk about the solution of equation number 1 which we developed previously, so y naught into integration factor is equal to integration factor dx plus constant. So this can be Ca is into t e to the power kt is equal to Ca naught t t e to the power kt dt plus integration constant c. And this can be written in more precise manner, t Ca naught e to the power kt Ca naught upon k e to the power kt plus C1. This is my equation number 2. So when t is equal to 0, Ca is equal to Ca naught. So from equation 2, from this equation, we can write 0 is equal to Ca naught upon k e to the power 0 plus C1. C1 is equal to k. This is my equation number 3. So again we take the help of this equation. Then this is T Ca e to the power kt is equal to Ca naught upon k e to the power kt minus Ca naught upon k. So T Ca e to the power kt is equal to Ca naught upon k e to the power kt minus t. Now further, if we go on carrying out this particular rearrangement, then Ca upon Ca naught is equal to 1 upon kt e to the power kt minus 1 e to the power minus kt, and this is equal to 1 upon kt e kt e minus kt, or C upon Ca naught is equal to 1 upon kt 1 minus e to the power minus kt. So if we put the value of this Ca naught over here and rearrange, then we find that this particular equation becomes 1 minus Xa is equal to 1 upon kt 1 minus e to the power minus kt. So this is my equation number 4. So now here we are given that k is equal to 1 minute per minute inverse, t is equal to 2. So if we utilize this equation, we may have 1 minus Xa is equal to 1 upon 1 into 2, 1 minus e to the power minus 2 into 1, and that comes out to be Xa is equal to 0.567, and that is my final answer. Now in this particular chapter, we discussed a variety of problems related to the space-time, etc., and we took the help of these two references which are enlisted over here, and thank you very much.